Okay. So in the previous lecture, we came up to this point. That is, we completed roadmap methods and we were about to take up the next family of methods, which is cell decomposition methods. Now, what is cell decomposition? The entire queue free, the free space, when you decompose into a number of non-overlapping regions, then you call those regions as cells and this operation as cell decomposition. This is segmentation of the free space into cells, and the cells will not overlap. Of course, they will share a boundary. Okay, so where one cell ends, if the domain continues, if the queue free continues, then another cell should start from there. So that is the way it is. So, and then their disjoint union will be the entire queue free. And if it is possible to cross over from one cell to another through the common boundary because of adjacency, then those crossing over possibilities need to be noted. And here now, rather than points, these big regions, these cells will become the nodes of the graph, and the crossing over probability possibility, that is adjacency, will give you the edges. Okay, so there is one cell which is India, another cell which is Nepal, and since you can cross from India to Nepal without passing any third country, we share a boundary. So then IN will be an edge. I will be one node of the graph, N will be another node, IN will be an edge. So the edge here actually has no physical length. Okay, and such a big region like a cell is actually reduced to a point in the graph. So, however, in such a scenario, the shape of India will not fit properly as the requirement of a cell, because a cell should be such that between any 2 points within the cell, the connectivity should cause absolutely no problem. Okay, but there is a difficulty in taking arbitrary shapes as cells. So as cell, you basically look for convex figures, okay, convex regions, so that between any 2 points of the region, the straight line segment will certainly be in the region. So that is the kind of things that you expect as cells. So neighboring cells having common boundary will give you an edge of the graph. Crossing over only between neighboring cells, because otherwise you cannot cross over directly from, say, India to Iran, right? So now these crossing over possibilities have to be represented in the graph as edges, and the way you decompose the region Q free into cells, based on that you can have different kinds of cell decomposition techniques. One is exact cell decomposition and the other is approximate cell decomposition. Now, exact cell decomposition is actually quite limited in its scope. So here the cell decomposition needs to be exact. Okay. So you cannot leave anything out and so on. And you cannot include anything which is not in Q free. So that is the idea of exact cell decomposition. And that will be possible only for very specific kinds of uh, free spaces or C spaces. To begin with, it will be operational only on in two-dimensional C space. It's not that in 3D space it is not possible, but it will have a lot of complications and you cannot work out a proper formulation. So for every new 3D region, you have to start afresh kind of thing. And the C-space boundary needs to be polygonal. Otherwise, you cannot talk of exact cell decomposition. And C obstacles also have to be polygonal. Polygonal is not a big issue, okay? And two-dimensional is a severe limitation. Okay? Now, suppose we have two-dimensional regions. Many algorithms operate in two-dimensional regions only. Okay, so and whatever boundaries we have, we approximate them with polygonal boundaries. Then, what kind of shapes you will take for the cells? Either you can have polygonal, then you will have the condition that they have to be convex. Okay, triangles are always convex. Otherwise, you can have a special kind of polygon that is trapezoidal. Okay, and trapezoidal has an advantage because you can operate with coordinate directions. Okay, so let us see one example of a trapezoidal exact cell decomposition. Say this is the region. This is outer boundary, polygonal. These are two obstacles, which are also polygonal. Okay, and here you decide to have trapezoidal cells and vertical trapeziums. You can decide. You could decide horizontal trapeziums also. In fact, for this example, I suggest that after seeing this example run through, sometime at your leisure, you work out a horizontal trapeziums for cell decomposition of this region. Okay. So for vertical trapeziums, what we do for all vertices, from all vertices of the outer boundary as well as the inner obstacle boundaries, you draw vertical lines. Okay. And we are following an XY coordinate system, so lines parallel to Y axis. And endpoints of these vertical lines, basically line segments, will be on the boundary of the C space or C obstacle. So see how it works. So this. And then this is the last boundary. So whether you draw a vertical line or not, it doesn't matter. Then through this, you draw a vertical line. Through this, you draw another vertical line. Through this, another. Then through this, another. Through this, also another. Okay, and so on. And then whatever trapeziums you get as cells, number those cells. Okay. Now here it has been numbered as this is C1, this is C2, and this is C3, and so on. Even if you actually number this as C1 and this as C2 and this as C3, it will not matter because in your record it will be like that. Okay. Now there are some triangles also here, but triangle is a special case of trapezium, so you don't mind. So after enumerating, you need to work out the now these C1, C2, C3, C4, etc. These will be the nodes of the graph. Okay, and the edges will be, for example, one edge will be C1, C2, because from C1 it is possible to go to C2 without crossing any other cell. They have a common boundary. Now, for a common boundary, edge is acceptable, vertex is not acceptable. Keep that in mind. Okay, say this is C2, this is C3, they share a vertex, but they are not called neighbors. Okay, because you have to go like this carefully. No, that will not work. Okay, so since these cells are two-dimensional entities, so their boundaries have to be regular one-dimensional entities. Okay, degenerate point will not work. So similarly, for 3D region, wherever they appear in our discussion later, perhaps, in 3D region, if you have a boundary which is a surface between two regions, two cells, that is acceptable as a boundary, and edge will not be acceptable. Okay, so the boundary must be of one dimension, just one dimension less than the region itself. That is the sense. Okay. Now C1, C2 is an edge, C2, C4 is an edge, C1, C3 is an edge, C4, C5 is another edge, and like that you work out edges. So through these edges you will basically get channels. So one channel will go like this through the, over the edges. Another channel will go like this. Another channel will go like this, and so on. Okay. So you develop the graph based on adjacency, and sequence of cells you work out as channels. Then when a query comes, when a pathfinding problem comes, okay, say you have a point here and here, then you first find out to which cell this point belongs. You find this point belongs to cell C1. Similarly, this point belongs to cell C15. Then you consult the graph, the channels, and find out a connection from C1 to C15, and you find that through adjacency we get a channel connecting C1 and C15 that goes over C1, C2, C4, C5, C7, C14, C15. Fine. Now the first edge will be C1, C2, C1, C2, right? This boundary. So this edge, for this edge, you work out the midpoint and connect this point, start point, to that midpoint. Okay. This is important because now crossing over becomes trivial. And then the next edge in the channel is C2, C4. So you find out the midpoint of the boundary of C2, C4, this boundary. Okay. So then this midpoint to this midpoint, to that midpoint, to that midpoint, to that midpoint, to that midpoint, to this. Now make note that this is not optimal. Okay. The visibility graph would give you an optimal kind of path, and that would perhaps go from here almost directly to this corner, and then to this corner, and then this. Or using the other channel, it could come like this visibility graph, and then this. But in a general methodology, you cannot do everything. Okay? So this is how the exact cell decomposition works. Now that is very limited. So the real tough business, big business, you can do with approximate cell decomposition. And here, the segmentation is something very fundamental. Okay, like trapeziums of this shape and that shape, so many special things you cannot handle here. So entire free space will now be segmented into simple and similar cells of specified shape. Okay, and cells must be non-overlapping as usual, sharing only the boundary, which would be one dimension less. Okay, and now since you will have all simple and similar shapes for cells, then it may be that part of the cell is occupied by an obstacle or anywhere falling outside the region boundary, and another part is in free. Okay, so that kind of thing is possible. On the other hand, there may be some cells which are completely blocked, completely filled, and then there are some cells which are completely free. So these are the three kinds of cells that are possible, and you have to mark them as such. So you have to flag completely filled cells, partly filled cells as mixed cells, and totally free cells as empty cells. So after getting the cells, you have to identify their type: filled, mixed, empty. Okay, filled are clear, you can't do anything about it, you have to avoid that region while path planning. Empty, that's what you like, through that you can plan your path. It is a mixed which is creating trouble, and we will handle it. So before handling that, it is possible to just design a system in which paths will be planned only through the free cells. See, in this example, this outer rectangle is the outer boundary of the Q free, and there is a triangular obstacle here. You can see the triangle? Yes. Now there is a thick, fat, L-shaped, oblique L-shaped object here, another obstacle, and this parallelogram is the third obstacle. There are three obstacles. And as you are see here, all the cells are of the similar shape. Okay, simple rectangles, all rectangles, and similar. All rectangles are similar. Okay. So through the green rectangles, which are completely free, you need to plan a path. Okay. The black rectangles in the or black cells in the cell decomposition are completely filled. Red ones are mixed. Okay. So in the path planning, you try to avoid black ones as well as red ones. Okay. You need to plan your path through the free cells only. Now it might happen that unless you keep your cell size sufficiently, and now you see, so this is only approximate description of the free cells possible. Okay, you cannot completely demarcate free and filled. You have to have something mixed if the region is of general geometry and your cell decomposition, your cells are of specific geometry. Okay, so that is why it is called approximate cell decomposition. You can only do approximate. Now you would notice that if the cells are too large in size, then you may have mixed cells which will block a lot of free space. Okay, and that may cause bottlenecks in the path planning. Okay, if you have too small cell size, then there will be too many cells, little cells. Okay, and that will make your graph enormous, and that will cause inefficiency. Okay, so what is the solution between the two? So how large to have, and what is the policy for that? How can you decide a policy on that? So for that, you decide on a hierarchical method: divide and label. Okay, so you reduce the error gradually by considering the mixed cells for further subdivision. Okay, and you can continue this subdivision of mixed cells only for several rounds. Okay, and after you divide a mixed cell into smaller cells, then each cell you examine separately and label them filled, empty, further mixed. These still mixed ones, little ones, will perhaps further be subdivided in the next round. So that way, those cells which got separated very early in the process, in early rounds, they will be big filled cells or big empty cells, totally empty or totally filled. On the other hand, mixed cells will get subdivided and produce more mixed and empty cells and mixed cells, I mean filled and empty cells, and some mixed cells also, which are smaller. So how small you go will depend upon the local geometry. Okay, this way, let us see first an example. Okay, so this technique is called quad tree. Okay, because it is in two dimension. Okay, so in two dimensional region, you can draw two lines and break things into four quadrants, and you will basically make a tree of these quadrants. So in a tree kind of graph structure, you begin with a root cell. So in the root cell, the entire free space must be contained, safely contained. In this case, the entire um, free space is actually contained within a rectangle, because the outer boundary is rectangular, but that need not have been the case. Okay, So in that case, you take a bigger rectangle which will safely enclose the entire free space and maybe something more. Okay. And that is the first cell, original cell, that is the root cell. And in the tree, that will be the root node. Okay. And then, since it is two-dimensional space, you break it up into 4 quadrants. That means this line midway, this line midway. So 4 quadrants you get. And each of the quadrants is a cell now in the next generation. And try to find out what kind of cells these 4 children are. So each of the 4 turns out to be mixed. And then since each of them are mixed, so in the next round you have to subdivide each of them into further 4 quadrants. So this quadrant of the first generation is subdivided into 4 child nodes. Okay, and now one completely free cell emerges here. From this subdivision, 2 free cells will emerge. From this subdivision, 1. Okay, and others are still mixed. So this picture shows you the snapshot after 2 rounds of subdivision. Okay, 2 rounds of decomposition of mixed cells. Okay, now you label these as free, 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 and other cells as mixed. And in the third round, these mixed cells will be further subdivided, right? And you are constructing the tree actually. You are keeping the record in the data structure of a tree in which the first root node mixed. Then below that, 1, 2, 3, 4, 4 child nodes each mixed. Then in the next, each of the child nodes, each of the 4 child nodes will have 4, 4, 4, 4. Okay. And then some of them will be, those nodes will be, some of the nodes will be free, are free in this case, and others mixed. Then the free nodes will not marry. Okay. So they will not have children. So the child nodes, of course, marriage is not there for child nodes also. This is just bacterial kind of reproduction. So each of the mixed cells will reproduce and produce 4 children. Okay, and the picture is here. Now, this mixed cell, for example, produces upon decomposition 2 free cells and 2 mixed cells. On the other hand, this mixed cell produces 1 filled cell and 3 mixed cells, and so on. You will see so many green things have appeared and 1 black has appeared, which is completely filled. Then you go on. Now the logic is clear to you. You get this. Another round, you get this. So over generations, you start capturing the boundary more and more closely. Okay, and how many rounds you will have, that depends upon your tolerance requirement. So if you say that I'll never go below half millimeter, then by the time one of the dimensions of a mixed cell becomes half millimeter, after that you will not further decompose. That much accuracy is good enough for you. And how much tolerance you want, how much accuracy is good enough for you, that you will decide. Okay. So this way, what will happen is that these huge free cells will not require a lot of storage, and each one of them will be sitting as just one node in the graph. Okay, and therefore the graph will not be unnecessarily loaded. So you will save memory, you will save processing. Okay. On the other hand, still you will be capturing the complicated regions in the boundary. In fact, this was not very complicated example, but you have got the picture that in very complicated examples also you can handle them with this manner. Okay, so this is what is known as the quad tree decomposition. And then the rest of the planning business goes like any cell decomposition, because between cells you have edges which are the over common boundaries, and you have a graph. Okay, in this case tree. Okay, so you know now which ones are, I mean, in the cells you have a graph because this is connected to this. Okay, and the data about different cells are there in the tree structure, from where you can collect whenever you want. And the actual path will then go over the free cells. Okay. Now, since this was two-dimensional, each time you decompose in four quadrants, out of which you make the tree structure of data. So that is why it was called quad tree. Okay. So nodes of the tree are cells. Root of the tree is the root cell, which has the full region, and every mixed cell has four child nodes, say northwest, northeast, southwest, southeast. Like this only, if you are doing in a three-dimensional region, three-dimensional C space, then you will talk about octree. Okay, because now at every round you will be decomposing a mixed cell into 8 octants. Okay, so a tree of octants is called octree. Okay? Similarly, in the n-dimensional case, you will have 2 to the power n tree, and that must inform you that this method, approximate cell decomposition, is general. You can apply it for C space of arbitrary dimensions, and that is a great advantage. Such methods we specifically value. Okay. A question arises whether it is a complete method or not. Okay. And in this context, we can talk about a new concept. You see, if you require a tolerance of say half millimeter, but in your decomposition, in your quadtree or octree decomposition, if you have kept a tolerance of 2 millimeters only, then your cells are sometimes not enough, you know, small that would allow a path which would be actually possible. So that's what I mean when I say if you really need half millimeter tolerance, but in your decomposition, if you have kept 2 millimeter tolerance, then a situation may arise that an existing path you fail to get through this method. But then, how much resolution to use for the method, that is actually in your hand. So if you reduce the resolution, then it will be complete. On the other hand, if you don't reduce the resolution, then it will remain incomplete. That an existing path it will not give. So if you have a situation like this, then you see that if I am free to reduce to refine the resolution to the extent I want, then the method will be complete. So such a sense of completeness is also talked about, and then this method is called neither complete nor incomplete, but resolution complete. You put a hyphen between resolution and complete. So it is a method which is not complete in general, not incomplete in general. It's a resolution complete algorithm. So this is a complicated concept. That is why we did not talk about it earlier. Okay. Now we go to the next family of methods, which is potential field methods. Here I'll take a little 1 minute break and come back. Okay. So the potential field methods are actually, in a way, the simplest kind of methods that you can think of from a school physics background. You want the robot to reach the goal, and you want the robot to avoid the obstacles on the way. So the simple thing that you can think of is that in the C space, the robot is anyway considered as a point. Okay. So you consider that as a point charge with positive charge. Okay. And for the goal point, you design an attractive potential as if a negative charge is sitting there. So the goal will attract the robot, and then for every obstacle inside as well as on the boundary, you devise some positive potential, positive charge. Okay, positive charge or potential, whichever way you want to do. Okay, either you can put a charge distribution, or you can directly propose the potential function. Okay, and by designing or devising such artificial potential fields, you develop artificial forces which you can calculate. Actually, such forces will not operate on the robot, but with these potentials, you can work out their field intensities, and based on that, you can work out artificial field forces, which will make the robot navigate through the free space up to the goal point. Okay. Like this. Say this is the start point. Here the positively charged robot stands, and suppose this is a goal point, and these are two obstacles. These are outer boundaries. This is the outer boundary. So for the outer boundary also you will need to design some potentials, but here those have not been included. So you describe the C space with the help of the potential functions U from Q from Q to R. Okay, for every point, every configuration Q in the C space. Now take an example of an attractive potential for this, okay, which is something like half xi times Q minus Q goal square. So you see, it is not an inverse square law. It is simply square law. Okay. So this gives you a paraboloidal shape of the potential function. So if this is the goal point, then at this point, the lowest point of the paraboloid will be, so see the 3D plot here, okay, like somewhere here. And as you go far, the potential function will be more. So this is the shape of the potential function paraboloid, because we have designed the attractive potential like this. And this will actually operate negative. Okay. Here only the magnitude has been shown. This xi is a scale factor, as you understand. And for the obstacles, you have to put a repulsive potential, repulsive field. So repulsive potential you rep for the C obstacle, and you keep that in infinite inside the obstacle. Infinite means what? Computationally, you will put 10 to the power 10 or something like that. Okay? And you have to design a function in such a manner that it is it changes from that infinite huge value to very small value within a small distance. So that small distance you take as d0, and then say if the separation of the configuration q from the boundary is less than equal to d0, then we use this as the repulsive field, repulsive potential. On the other hand, if it is more than that d0, that threshold beyond which you don't want to apply any field force, okay. So if the wall is something like 1 foot away, then you don't have to bother about the robot hitting the wall. Okay. So only when it comes within 1 foot, then you say that no, no, now start, the wall should start repelling him. Okay. So dq is the clearance of the configuration q from the nearest obstacle. And here also you have a scale factor eta. And now you compose the repulsive field and attractive field together. So this will be negative and this will be positive. And as u is differentiable, this you have managed a differentiable potential field. So the force vector will be equal to the negative gradient, and the robot will follow this negative gradient direction and proceed towards the goal. This is the sense. Okay. So this is the potential of the obstacle. This is the contour, actually combined contour. Okay, this is the potential, combined potential, obstacle and the goal. That is why this side is a little up. Okay, and here huge plateaus are there. Okay? So as you see this 3D plot in the form of contour, then this is how contour should look like. Okay, this is the low value, values going higher, 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 and so on. Okay. So from here, if you follow the negative gradient, cutting these contours perpendicularly, then you reach the goal point. So incremental steps you take in the negative gradient direction, and it is a real-time process. That is, the DQ, that is nearest obstacle, will be found by sensors, and based on those sensors, this formula will take over and give you the step. At that step, you go a little, the robot goes a little, you design that how much, what is the step size. After which, the new sensory data will be used as the position and direction of the nearest obstacle, and accordingly, the thing will work out. Okay. So this is the sense of the potential field method. Now, in simple C spaces, it will work also, the way this example shows. However, in complicated regions, this may create problem. For example, just in front of you, if there is a little wall, okay. On the other hand, your goal happens to be on the other side, okay, behind this little wall, and this wall is not continuous, endless. You can take a detour, okay. So detours are possible, but then if you operate with this kind of field structure with the direction of motion given like this, then what will happen? Then that goal point behind the wall will attract you, and the obstacle itself will repel you when you come very close. Okay. As long as you are not very close, that will not have any effect. So you start coming closer, 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 till you come at a point where that will also start repelling you, and the goal is still attracting you. So you will go a little further. And then when it happens that the goal and obstacles, attraction and repulsion, balances exactly, okay, then this gradient will be zero. Because you know that at the stationary point of a function, you have got its gradient as zero. So when that attraction repulsion fields exactly balanced, then this will turn out to be zero. And at that point, the potential function will have a stationary point, okay, and perhaps a local minimum. That's not, and you are basically looking for the minimum of that potential function by moving like this, and that will have a local minimum. And this is a problem. Okay, this is a standard problem in potential field method. So potential field method alone is not reliable, because then the robot will get stuck. If you rely completely on this method. So in that case, you think of what can be done. Then these are the possible things that you can do. One is navigation around the neighboring obstacle. Okay, that is something which can be coded as a real-time process. Okay, when the robot is actually operating, but it will delay things. Okay, unforeseen, unplanned delay. Okay, a definition of a new potential function you can do, but for that you can never a priori decide all possible kinds of geometries. Okay, so that's a problem. Random deviations is something which is suggested, that take a flip, move in some random direction which is free, and then from there you restart. So that is also arbitrary and time delaying proposition. You can think of incorporating global considerations. Okay. But the moment you talk of incorporating global considerations, that stops the idea of the real time process. You cannot take care of global considerations in real time. So you have to offline beforehand plan the thing. That means you have to beforehand know the C space completely. And the special advantage of the potential field that with which it was originally, you know, um, made popular, that suffers. However, since the other methods are offline, you say that offline methods are not that bad. We don't mind using them. Let us see how it can work. So one thing you can do is that you can combine potential field methods with cell decomposition. And that's a good way of using it. Based on a rough knowledge of the C space, you work out a plan according to your cell decomposition algorithm and keep that plan and try to follow that plan in practice when the robot is operational. But then, based on sensory data, take corrective action using potential field based method to handle contingencies arising out of the prior knowledge of C space not being exact. This is how you operate, you as a human being, this is how you operate when you go to a previously unknown, unvisited place. You go with a map. Say you are going to Vienna for sightseeing. Here, this church is there, which is very old. We have to see that. And there, at that point, Mozart's memorial is there. We will see that, and so on. Like that, you work out a plan and start operating with that. And then when you go there and you find that there are buildings in between and some geography has changed after the map was made. Okay. So according to that, you use your eyes. Okay. And you ask this man, that man, these are sensory information. Based on that, you fine tune your path. So this is what this combination with cell decomposition does. This is a practically useful method. Offline applications of potential field methods use actually computation intensive kind of considerations, and there are quite a few of them possible. Actually, these are our group's research contribution over last 15-20 years. One is variational formulation. Okay, work out the path symbolically, including the necessity of short length as well as the obstacle avoidance and reaching the goal point. Okay, as a continuous path, a continuous function of a path parameter u. Okay, and then ask it to satisfy a variational principle which says that the action, which is the integral of a Lagrangian defined using the geometry of the C space, is minimum. Okay, the action is the integral of the Lagrangian, okay, over u. So this is one way which we have found quite successful in getting paths in very complicated regions. We have some of the publications which sometimes you can see at leisure if you are interested. Then we also work out a global navigation function. That is, we define, this is another series of um, works that we did on this idea. For that, we say that we will design a function which will be a Laplacian function, and for which we handpick the boundary conditions. Okay. So boundary condition of the goal we put as 0, and boundary conditions of all the obstacle boundary points we put as 1, and then based on that we work out the potential of the entire region. And since the Laplace equation cannot have a solution, there can be no Laplacian function which has a minimum or maximum at an interior point. So the only minimum will be there, and only maxima will be at the obstacle boundaries. And in between, you will have contours of the function which have, one enclosing another kind of thing, and from any point you will get a direct route. So that we did not a priori design the repulsive and attractive potential field, potential functional forms, but we said that the functional form will emerge as the solution of that boundary value problem, solution of that Laplace equation. This is what we did in another kind of work. And the third approach says that based on this kind of an activity, by solving a potential function, we are actually designing a potential function which has a minimum at one point and maxima at the boundaries. Okay, so like that, we can actually say that now the entire domain, entire Q free, we can map to the interior of a sphere with the boundary of the region, mapped to the mapped to a sphere, and one chosen shape center of the region is mapped to the center of the sphere. Okay. Like that, what happens is that whatever may be the original shape of your domain, that gets converted to a spherical shape, which is convex. And then in this mapped domain, between any 2 points, you can plan a straight line path and then use the inverse of the mapping to get that path inverted to the original domain. And this kind of a path shows a remarkable property that it turns mostly because of obstacles, otherwise it tends to go relatively straight. Okay, so that is the thing that you really needed, which in these two methods also we try to propose. However, the domain mapping is quite computation intensive. All of these are computation intensive, and so they have to be done offline. Okay, so you cannot do that computation when the robot has started operating, okay, on a second by second, millisecond by millisecond basis. So, but these are good methods which can be useful. Okay. Now, before we finish, we also discuss one more roadmap method, which is probabilistic. This I feel necessary to discuss because this is a conceptual change which you should register. So, probabilistic roadmap method is a method similar to conventional roadmaps, but the nodes of the graph are randomly selected from Q free. Starting from a point, you can say that nearby 3 nodes I will explore. If the nodes are free and the direct path to these neighborhood potential nodes are completely free, then we connect them as edges. We take 3 nodes and so on. In some cases, all 3 will not be free. For example, the third one in this case, say from here you come from this earlier point, and then from here again you construct a tree basically. Okay, and then connect the nearby fellows through the graph. Then from here, the new 3 that were generated, perhaps one was here, another was here, another was here. So these 2 you connected because the paths were free. This little path was crossing through an obstacle, so you did not connect it. Like this, you go on trying neighbors and incorporating them in the graph if they are fine, if there is continuous path between the 2 points. Like that, you construct a roadmap probabilistically. Okay, so every node is connected with neighbors, as long as the connection intersects no obstacle. Number of neighbors, you decide, because for example, I said you pick up 3 neighbors. You can choose 2 or 4. Okay, so it's up to you. Now, later also, if you want to refine or extend the roadmap, you can do that by taking nodes and picking up more neighbors. There are several possible strategies to decide on the way to locate nodes and connect them. That is detailed. You can work out whichever way. There are several publications which suggest several ways. Okay. And once the roadmap is built, the rest is the same old graph search. And from the queue start, you connect a nearby point to the roadmap and then go along the roadmap. And then finally the queue goal you connect like this. Okay. So basically the queue start and queue goal, you connect to the roadmap, which forms the first and the third segment of the path. And the in between major part, you work out by graph search. So this again, if you ask whether it is a complete method or incomplete method, then this is called probabilistically complete. And that means that by playing on the number of nodes that you are ready to give, you can increase the probability of success of finding an existing path to any number that you want. Say, for example, I say, I want your path to succeed with 90% probability. Then you say, then I will take these many nodes. Then I say, no, 95%. Then you say, okay, then I will have to take more nodes, which is this. So like that, if you can handle the thing, then it is called probabilistically complete. You can meet the demand of any probability of success. Okay, still a little probability of failure remains. Okay. So now we compare the methods in a nutshell. Roadmap methods, visibility graph, reduced visibility graph, and generalized Voronoi diagram, they are operational on only two-dimensional C spaces. Silhouette method is applicable on arbitrary dimensions. Cell decomposition, exact cell decomposition is operational only in 2 dimensions. Approximate cell decomposition can operate in any arbitrary dimension. Potential field methods, whether it is the local original kind of thing or with global considerations, in each case they can operate in arbitrary number of directions. I mean arbitrary dimensions. These roadmap methods are typically complete, except probabilistic roadmap method, which is probabilistically complete. Cell decomposition method exact, which is limited, but in that limited scope, it is complete. Approximate cell decomposition is, we said it is called resolution complete. Here it is written no, but the detail is that it is called resolution complete. Potential field methods, the local ones are not complete, global ones are. Okay. Roadmap methods give you this visibility graph method gives you optimal path. Generalized Voronoi diagram does not give you an optimal path really, not the shortest path, but in one sense, it institutes an optimality. That is, it works out an optimal mix between two ideas. One is staying equidistant from neighborhood obstacles and then going as straight as possible. Cell decomposition methods are typically not optimal. Okay. Potential field methods, the local ones are not optimal, though they actually look for an optimal point of their potential function, but that is very indirect. Global methods are optimal in a sense, like this. Okay. Now, different methods have different computational complexity for which we actually did not conduct the analysis because that is too complicated because there are large number of indices involved. Okay? Dimension is one, and then there are others. And now we come to the point of the extensions of the basic problem. The basic problem was a single rigid body in a known geometry of a known geometry in work cell, the geometry of which is completely known and so on. Okay. Now, one is, what about obstacles that can move? Okay, moving obstacles. Now the question first arises, do you have a priori knowledge of their motion? Do you have their motion as r of t? Okay. In that case, you can incorporate that in the plan. That is one thing. And in any case, time will enter into the analysis just like the space variables. Earlier, time was not there. For description of the path, we did not say that the path reaches this configuration at this time, this configuration at this time. We parameterize that with respect to a path parameter. Okay. Now time actually operates in a clear-cut way because the obstacles that move, they will move in time, and we have to handle time also as a dimension. So basically, now we cannot work out our thing in the n dimensions of the C space. We have to operate with n plus 1 dimensions of the configuration and time. So that is called CT space. Okay. And here there is an important issue. In C space, in geometry, in X, you can go forward as well as backward. But in time coordinate, you can go only forward. Okay. So that is one thing which you have to keep in mind. That is, a later configuration has to be later. Okay. So the sequence of configurations from C0 or Q0, Q0 to Q1, Q2, Q3, Q4, whatever Q4 is, its time coordinate should be higher than the time coordinate of Q3. Okay. So in time coordinate, you can go only one way. One case of moving obstacles is the case of multiple robots. That's actually very popular because in the popular robot soccer games, you encounter other robots which are all like obstacles. Whether the other robots are of your own team or from the opponent's team, all of them are obstacles for your motion. Okay. Articulated manipulation robots actually will be another kind of situation where the other links of the manipulator will operate as obstacles for each link. Okay. The immediately connected link will not because the joint is appropriately designed. Okay. But the later ones, it will be an obstacle. For example, link 2 of a serially connected articulated manipulator, link 2 and link 4 will be mutually, operating as obstacles for each other. Link 2 and link 5, they will also. Link 2 and link 6. Link 2 will not have any fuss with link 1 or 3 because for them the joint was designed in such a manner, because that is a single degree of freedom motion, so that you can settle at the time of design itself. And for the articulated manipulation robots, the C space configuration space scenario is peculiar. Okay, if you try to plot it, you will see. Okay. This was the situation with moving obstacles. Now there can be movable obstacles. That is, the obstacles are not moving on their own, but they are small enough and light enough that if the robot needs, it can move them. So these are movable obstacles. For example, when you are operating in a cluttered room, like my room here, okay, of course you are not seeing it, or you're in your classroom where there are chairs. Okay. So if those obstacles are movable, if you can pick up a chair. So for example, if you are trying to move from one place to another in this room of mine where I'm giving the lecture, in between you cannot see, but I can see there is a chair there. Okay. If you are fat and if I have kept the chair in a bad manner, then as you want to come to me, you will find the chair in between. Now the chair is very light and that is movable. So you can decide that I move this chair to the right side and then I proceed. Okay. So if you can give such authority to the robot, then on the way, whatever little object it finds which it can move away to get its path, then that's a case of movable obstacles. Obstacles which can be moved around. And for designing a path, for planning a path, such objects are moved by the robot. So this produces another issue in the path planning business. So of course it makes more paths possible. Okay, an obstructing obstacle is removed from the way, and the robot enjoys a path which otherwise would not be possible. But operationally and algorithmically, it brings in another issue, and that can be handled, but some effort is required to do that. Then there are kinematic constraints. Okay, that is actually very funny. It may happen that the C space is three-dimensional. Okay, but the motion possible motion is only two-dimensional. So, for example, you need to go from here to there. Say you are with a car, okay, or with a scooter, even bicycle. Okay, so you have to go from here with this configuration at this point, at the starting point, and you have to end at that configuration at the starting point, at the ending point. So suppose you are going to park your car. You are inside the car. The car is in this place. A, B, C, D are the locations of the four wheels, and you have to go to the parking place and park exactly at A prime, B prime, C prime, D prime wheels. Okay. Now you can do that. Whatever x, y, theta I give you at this end, and whatever x, y, theta I give you at that end, you can do this if you are a good driver. But then in the velocity space, the motion is not three-dimensional. The steps, the delta steps that you take to go from this xy theta to that xy theta, that those steps will not be three-dimensional in space. Okay. So x dot, y dot, theta dot, you cannot have arbitrary because it's a wheeled vehicle. Okay. So that is why parking in a narrow parking space is a problem. Okay, so you cannot have arbitrary velocities. You have to go this way and then adjust and then come reverse and then go like this and so on. And this is an additional headache for planning. You have to work out such possible 2D motions which allow you a gross motion in 3D. Okay, it is possible, but that has to be handled. This kind of constraint is typically non-holonomic, okay, which cannot be integrated. And this is what I was trying to tell you, that in the velocities, there is a constraint, that is x dot, y dot, theta dot are related among themselves. You cannot integrate that and get a similar constraint in x, y, theta. If you could get, then the C space actually would not be three-dimensional, it would be two-dimensional, because then all x, y, theta would not be possible. So this is a non-holonomic constraint which cannot be integrated. If it can be integrated, then it's a holonomic constraint. Okay. And that also happens when you have a closed loop kind of chain, okay, closed loop manipulator. There, the motion description may require you to take more number of coordinates than the degrees of freedom. Okay. And then among those coordinates, there will be a relationship. You know about 4-bar mechanism, for example, 4-bar, 5-bar mechanisms. Okay, so their kinematic equations appear as those constraints. So those are integrable constraints where the constraints in the theta dots can be integrated and you get a corresponding constraint in the thetas also. So those constraints also have to be handled. Okay, so these handlings will require some additional work which is beyond the basic problem. Then there can be uncertainties. For example, the task of the planning may be rough. For example, the kind of example is that when you plan your motion from wherever you are to the railway station for catching a train, okay, basically you do not plan the motion from the chair in which you sit to the specific door to the of the train through which you enter your coach. You plan the motion from your hostel to the railway platform, okay, railway station platform, and there is a lot of uncertainty. This is one kind of uncertainty, modeling uncertainty, because a priori you don't know from which point you will start in your house, okay, or hostel, and at that end you don't know at which point your compartment will come. This is modeling uncertainty. Okay, in between also the modeling of the path may have certain uncertainties. Then there will be sensor uncertainties, okay, and control uncertainties. So in spite of such uncertainties, if you can always make a plan which works, okay, then that will involve more considerations, more issues to be handled in the path planning algorithm. So these are some of the extensions which are there in the basic problem in the practical ones. Okay. So in summary, what we have discussed? We have discussed the basic concept of motion planning in robotics, including its mathematical formulation, the C-space modeling, and roadmap, cell decomposition, and potential field methods. Briefly, we compared the methods, and then briefly we discussed the extensions of the basic problem. Okay. Now, if you want to study the subject matter, then where to go? These two last ones are single chapters in robotics books. One chapter in Schilling's book, and then there is a chapter in Richard Murray's book, Murray, Lee, and Sastry. Okay, so in this book there is a chapter on robot motion planning. These books are completely on motion planning. This is a modern book which is good as a textbook. Okay, this Joseph Lynch, Hutchinson, Cantor, Burgard, and Kawraki, and Thrun. Okay, there's a lot of authors. Okay, so this is a reasonably good book. Okay, simple enough, but not trivial. And competing with this book, there are other books like this Computational Principles of Mobile Robots and this Planning Algorithms. If you become a real expert, then one day you can think of reading this book by Latom. When I started, this was the only book, and this is written, I mean, this has a lot of material, but it is written in a very complicated mathematical computer science kind of language. In fact, first time when I taught this course, the task between me and my students was that together we will study this book and try to understand what it is. Okay. And because before that, I also did not study robot motion planning, the students were anyway new. Okay. So during that semester in 2001, I and students together tried to decode the book by Latom. There was a time when this was the only book of robot motion planning. Okay, you can see the year. This is 93. All the other books are later. Okay, Shastri's book is among them oldest. Even that is 94. Okay, so this is the first book of robot motion planning, but it's a classic book. Okay, so 2001, I first taught a full course on robot motion planning. At that time, I actually learned the subject, and then year after year, many years, I taught it, and the material got more refined. So for this material, my thanks are to the audience of my classrooms of all these cases, and in particular for these slides, my special thanks are to this gentleman, Dr. Habil Dietmar Tutsch of TU Berlin. At that time, he was in TU Berlin. Now he is somewhere else. Okay. In fact, he was in my Berlin class of 2005, after which he prepared the original version of these slides, which was in German. And now and then I guided him a little. And after that, I took the slides from him, and with his permission, I converted it into English, which is the version that you see, and removed from that many things which I did not want, and added 1 or 2 things which I wanted. Okay, so that final version was created in 2006. That is why you find that after the classrooms of 2006 onward, that is after 2006, are not mentioned here. Okay, so this is the overview of road motion planning that I wanted to give, and for your own study, you consult these two and perhaps somewhat of this, to the extent that you can handle. All the topics that I have discussed, you will find in this book certainly, and in these two also, most of them. Okay. Okay, so we stop here, and in the next lecture we will continue with redundancies. Thank you.